This is the outline. So first of all, I will talk about what is the definition of the differential equation and what is linear differential equation and more. And finally, I'll talk about the constant coefficient linear ODE and there are some systematic method to really solve this kind of equation, the ODE. So first, let's see, 18 page. Yeah, so in mathematics, a differential equation is an equation that relate one and more function and their derivative. So I think in junior school, I suppose you learn how to solve the equation like something like 3x plus 2 equals 8, something like this. This is actually an algebraic equation. So in this equation, you can try to maybe subtract 2 on both sides, and then subtract 2 on both sides. Then this 2 and this 2 cancel, so we have equals 6 on the right hand side. So and then we can start to divide 3 on both sides. So that finally we'll get x equals 2, something like this. This is something called the algebraic equation, which means within this equation we only have algebraic calculation, something like plus, minus, multiply, division, something like this. So this is called the algebraic equation, and probably you should be able to solve this kind of equation in junior class, as long as this one is first order, and then maybe in junior 2 or 3 you learn how to solve the equation like ax squared plus bx plus c equals 0, something like this, and then probably you will get the answer like x equals minus b plus or minus square root of b squared minus 4ac over 2a, something like this. This is the general solution to this second order algebraic equation. And also you may be able to solve some algebraic equation like 3x plus y equals 2 and x plus y equals 1, something like this. Then you'll be able to subtract equation 1 by equation 2, and then you will eliminate y, and then you can solve x, and then you put it back the x value, and then you can get y. So in this case, we have 2 unknown variables, but still it is a first order equation, joint equation. So we're able to solve the equation. So this is so-called the algebraic equation, no matter if it is first order, second order, or whatever order, or how many unknowns. It only consists of an algebraic operation. And our target is to find the unknown variable. Something like x, y, or whatever variable. So here, a differential equation is an equation that relate one or more function and their derivative. So in the differential equation, the unknown is not a variable or variables anymore. It is actually a function. Usually a function of time or a function of the space or both. So in this case, we can see something like the equation can be like we have the derivative of a function. In this one, y will be a function of x. And we can take the derivative of y with respect to x. And then it relates the derivative and also the original function, also a function related to this variable, this independent variable. independent variable. So in this case, it is a equation including some of the derivative or even second derivative like this. So in this case, we will call it differential equation. And our unknown is not a variable or variables anymore. It will be a function or functions. So So here we talk about the ordinary differential equation. So an equation contains only ordinary derivative, which is like, suppose a function has only one independent variable. Then the derivative is a full derivative. If you have started to learn something like, for example, if maybe x is a function of s and t, and y is a function of s and t also, then as long as we would like to take the derivative, it is not the full derivative anymore. It is like partial x, partial s, or partial x, partial t, something like that. So this is called the partial derivative rather than the ordinary derivative. So this d is the ordinary derivative. So this is the partial sign. So it is the partial derivative. So ordinary differential equation means, for example, this x is a function of t. This y is also a function of t. So we have a full derivative of x with respect to t, and also full derivative of y with respect to t. And then this equation contains the derivative of the function and also the function itself, and maybe also related to the function of the independent variable. So an equation contains only ordinary derivative of one or more dependent variable with respect to a single independent variable. So here, y so maybe we can just separate. There are two different kind of variables. One is the dependent variable, and the other is the independent variable. So for the dependent variable and the independent variable. So for this one, y is the dependent variable because y depends on x. Y is a function of x. So in this one, we call y is a dependent variable and x is the independent variable. So in this one, still y is the dependent variable. Y is a function of x, and x is the independent variable. So we will say the first derivative of y with respect to x and the second derivative of y with respect to x. And for this one, x and y are also dependent variable. Or I should write it like x, y are dependent variable. X, y are all depending on t, which means x, y are functions of the time. And so the independent variable is t for the third equation. So here, for the ordinary differential equation, it consists only one single independent variable. So here x, t, and it may consist of one dependent variable or the function or functions, or even more dependent variable or functions. So we have one dependent variable for the first two, and two dependent variable or of two functions for the third equation. So this is a simple introduction to the ODE. So next we will talk about what is linear differential equation. So for linear differential equation, it is like, so here we assume the dependent variable is x, the dependent variable is x, and the independent variable is t in this case. So on the right hand side, it is only a function which correspond to the t only. There is no x term on the right hand side. So this is all independent variable, the function of the independent variable on the right hand side. And on the left hand side, it consists of x, xt, dx dt up to dn x dt n, the nth derivative of x. So yeah, so an nth order ODE is said to be linear if the function f is linear. So it's just like, it's very stupid. This is linear if the function f is linear. And yeah, and actually this equation can be written as this case, So we will have the n derivative, n minus 1 derivative up to the original function. This is the first derivative and the original function on the left hand side. And there are some coefficient. There are some coefficient for each term. It is just like when you solve the algebraic equation, something like you have a2 x squared plus a1x plus a0 equals 0, something like this. Or maybe you can just add more up to an x to the nth power plus dot dot dot. Then it is a nth order algebraic equation. Of course, if n is high enough, then it doesn't, there isn't necessarily the closed form solution. As n is more than 4, then there will be no general solution. Yeah. And here, if it is a linear ODE, then the coefficient can only be a function of the independent variable, which means this is an of t, an minus 1 of t, a1 of t, a0 of t. So this is only function of time, and here multiply by each of the derivative. For example, so y double prime means y double prime means d2y dx2 here. Of course, it does not show the independent variable. It may be x or t, doesn't really matter. But for this one, x superscript third means dx, d3x, dt3, something like this. So the third derivative, we will use this bracket to represent this. If it is more than 3, probably you will use this bracket. Otherwise, you will need something like x prime prime prime, or fourth power will be like, then it will be very strange and difficult to read. So we'll use this bracket to represent the order of derivative. Yeah, so this is an example. So this is a second order. We will say nth order if we have the nth derivative. So this is a second order ODE, And the coefficient, this is 1, this is -2, this is 1. So it is a constant function, of course a function of time. And for this one, this is a third order ODE. So on the right hand side, this is a function of the independent variable exponential to t, exponential to t. And on the left side, it consists of the third, up to the third order derivative. So this is a third order ODE, and the coefficient for the third order term is 1, and the second order term is 0. We don't have x double prime, so it is like 0 times it, and this is not a constant anymore. It is 3t, but it is a function of the independent variable. So it is still a linear ODE, and for the original function, the coefficient is -5. So this is still a linear ODE. Still, linear ODE is not easy to calculate generally. So here are some counter example. So we will see nonlinear ODE here rather than linear ODE. The other way around is nonlinear ODE. So here, for this term, we have x times x prime, especially this term, minus x times x prime. So this is not linear. The linear requirement is like we only have each term multiplied by the coefficient, which is only related to the independent variable or function of the independent variable. But we can't really have x prime. And in this case, this is a nonlinear ODE. And here, this term sine x is of course a nonlinear function. If you have learned the Taylor series, you know that sine of x is actually x minus x cubed over 3 factorial plus x to the 5th power over 5 factorial minus x to the 7th power over 7 factorial ... up to the infinity. So this is of course a nonlinear function, because we will have something like x cubed, x to the 5th power, x to the 7th power. Don't mix up with this one. This is a derivative. We can have nth derivative, and it doesn't really it will still be a linear function, but x to the 7th power, x to the 3rd power, x to the 5th power, x to the x squared is still a nonlinear function. Only x itself is linear function, or maybe x times another constant, or maybe times the independent variable. So sine of x is not a linear function, and here x to the 4th power, x to the 4th derivative, the 4th derivative of x is linear, but x squared is not linear. So this is 3 examples of the nonlinear ODE. Okay, so next. So when we talk about linear function, of course, this one is an explicit expression for the linear ODE. But here in the definition, we'll say this is linear ODE and this is a linear function. So a function is linear means when we act this function, actually generally we'll call it a functional rather than function, because the argument of it is a function. So this is some sort of a functional, but it doesn't really matter. But yeah, so the definition for linear function means it should satisfy this this expression. It looks quite complicated. It is like f of this one, a1 x1 of t plus a2 x2 of t equals a1 times f of x1 of t plus a2 times f of x2 of t. So it's something like that, and and for all a1 and a2 are arbitrary real number, it should satisfy this this relationship. Then we will call f is a linear function. So I can show you a special case, which is like if a2 is 0, a special case, then if it is a2 is 0, then this term is vanished. So we have f of a1 x1t equals a1 times f of x1t. So this is called the in a simple interpretation that this is linear. This is linear. We can just put this value out of the function. It's something like that. We have f of a1 here times x1 of t, and then actually we can put this a1 out of this one. Then we'll call it linear function. And another special case is that a1 equals a2 equals 1. So in this case, it will look like f of x1 of t plus x2 of t equals f of x1 of t plus f of x2 of t. So it is like you add two functions together and then put in this function. The output will be like you put in one of the function to this f, and then put the other function to this f, and the output you add together should be the same. So it's just like you break the function into two parts. So this is called a superposition. So maybe I can ask you something. So so now I just talk about this one. Maybe I just copy it. Here we have this one. So let me consider some of the function. So if just say if we have, so for example, f of x is 3x. So you suppose this is a linear function. So now if x is just say 4 times of x of t, something like this. So on the left side, if I call this one equation 1, this is equation 2. So if I just put this one into equation 1, on the left side we have f of x, f of x, is this one put into here. So we have 3 times 4 x of t, which is 12 x of t. If I put it on the right hand side, it will be like a1f xt, which is like 4 times 3 x of t, something like this. Yeah. Because here we have a1 to be 4 here. So when we calculate, this term will be like 3 times 4 times x of t, which is 12. And when we calculate this term, which is like a1 is 4, so we have here times it. So we still have 12 x of t. So these two, so it satisfies the linear property. And if we have x to be x1 of t plus x2 of t, so in this case, f of x will be 3 times x1 of t plus x2 of t, something like this. So we have 3x, f of x is 3x. So, and the other case is f of x1 t plus x2, plus f of x2 of t. So we'll put x1t into here, so we have 3 times x1 of t plus 3 times x2 of t. So of course these two are the same because we just fracted these 3 out, so these two are the same. So we say this is a linear function. And yeah. So how about another one? If we have, let's say, still x equals f of x equals 3x, and then now we have maybe 3x plus 2. 3x plus 2. Do you think this is a linear or non-linear function? It looks like it is linear because when you learn the analytic geometry, it is like y equals 3x plus 2 is something like this way. Y equals 3x plus 2. It is a linear. The shape of this equation is a line, is a straight line. So you may feel that this is a linear function. But yeah, let's see. If we plug in capital X to be 4 small x of t. So as long as we have f of capital X, it is like 3 times 4 x of t plus this, like this, because we just put this one into here. So we have 3 times 4x of t plus 2. So it should be 12 xt plus 2. Now if we have 4 times a1 times f of xt, because here we should have a1 f of small x of t. So it will be like a1 is 4, so we have 4 times f of small x is 3 x of t, because we plug in x of t to be here, so we have 3x of t plus 2. So it is like 12x of t plus 8. So they are not the same. They are not the same. So actually, this is not a linear function. This is a nonlinear function. This is a nonlinear function. And even for the superposition, it will not satisfy both these two equations. You cannot satisfy both of the condition. So it's a nonlinear function. And maybe I can also give another one, which is like f of x to be x squared. So now we still have x to be like 4x of t. Or maybe I put it to be 5. Because in this case, a1 is still arbitrary number. A1 is still arbitrary number. Yeah, so yeah, so f of x is like 5x of t quantity square, which is 25x of t square. And yeah, and now if we have a1 x f of x small x of t, so we will have 5 times x of t squared, which is 5x squared t. So they are not the same, so of course x squared, x cubed, or even x to the nth power, as long as n is not 1, then all of them are not linear function. So this is nonlinear. So this is yeah, some interpretation to the linear property, and you can actually use this to check whether a function is linear or not, and probably most of the functions are not linear. Yeah, so also you can use this property to check whether this ODE is linear or not. As long as you can just plug in maybe x equals to a not a, maybe you just put in a b here, b times x 1, b times x1. You can just put in there. It is just like a function, and then it is actually like you put in b times x1 to replace all the x there. Then you get the factor of b. You get the factor of b, which is like this expression. Or you can use another substitution, like x to be x1 plus x2. X to be x1 plus x2, and then you plug into this equation, and actually, as long as we have a dx dt should be like dx1 dt plus dx2 dt, something like this for derivative. It is actually linear, so you can just separate all the term apart, so you will have f of x1 of t and f of x2 of t, something like this. And definitely you can really prove that this is a linear expression. This is a linear function. Okay. So up till now, any questions? No questions. Okay, so so we have a special case for the linear ODE, which is the constant coefficient ODE. So for this case, it will be solvable, no matter what its order is. Yeah. probably in the course or in the exam, it will be not more than 3. I think. Yeah, unless the equation is the coefficient is very special, then even higher order can be solvable. But generally, if I need to test whether you know it or not, then second order or even third order should be quite sufficient. So for the constant coefficient linear ODE, it means that if all the coefficients in the linear ODE are constant, yeah, so it's straightforward. It is what it writes. So it's called the constant coefficient linear ODE. So this is from the original linear equation, but the only difference is all the coefficient is not a function of the independent variable anymore. It is just a constant. It is just a constant. So in this case, it will be easy to solve. So this type of ODE is easy to solve with a systematic procedure. Of course, when you have not learned the something like the Laplace transform or Fourier transform, then you definitely will follow the procedure I'll teach you. And after you learn the Laplace transform, then you'll be able to solve even more types of linear ODE. Because what I teach you now, there's some limitation to the g of t. Some of the g of t on the right side, we can really think of the solution. And some of the strange function, then we may not be able to solve still, but at least for the left hand side, we have a systematic procedure to find the solution. And even though some of the function we may not be able to find the so-called the particular solution, still we can use some sort of numerical method to solve it. So it's still fine, but it already covers many types of most of the usual types of the function. So it will be good to go. Yeah, so let me talk about, let me finish this page first. So when we try to solve the constant coefficient linear ODE like this. So this is the constant coefficient ODE with the function on the right hand side. So the procedure first is to solve the homogeneous solution. So this is the first step, the very first step, to solve the homogeneous solution. The homogeneous solution means we let the right hand side to be 0. Just we move it. If it is already 0, then it is fine. And if it is a function of the independent variable, then we just discard it first. We try to solve this function. We try to solve this homogeneous equation first for the homogeneous solution. Yeah, so we will have an times dnx dt and up to a0x equals 0. We try to solve this one. Then after finding the homogeneous solution, and then we will try to find the particular solution for this one. The particular solution is for this one. So particular means 特别嘛，特别，so this is a solution specifically for this function, and of course related to this function, related to this equation. Yeah, find the particular solution. xp correspond to g of t. And then, so this is the homogeneous solution. This is the solution to this one, and xp is the solution to the whole equation. Then finally, the complete solution is just to add them together. Then this is the complete solution. So first step is to find the homogeneous solution. The second step is to find the particular solution, and the final step And the final step is to find the complete solution, which is just to add these two together. So it takes only 3 steps to solve a constant coefficient ODE, just like how to put an elephant in the refrigerator. It's just to open the door, put the elephant in, and then close the door, and it's done. So finally, we should use the initial value to determine the unknown coefficient. Some of the question we may need to use, because if we don't have initial value for the ODE, then probably there will be infinite many solutions to this homogeneous to this ODE. However, if there are some initial value to have been determined, then we can just limit the complete solution to be maybe only one or a smaller set of the complete solution. So 3 prime, some of the equation we need to do this, and yes, for some of the problem we don't really need to do this. But this is not so difficult. We just need to put in the initial value and then try to solve the undetermined coefficient. So let's take a 10 minutes break.